Okay. Now I hope all this is legible. I need to get a better way of handling the camera, but with my setup in here I don't have room to put it on a tripod. So I'll be working on that. Okay, anyhow, let's suppose, well, the next problem said, okay, what if we had these same 4 points and we wanted to try to fit them to a quadratic polynomial? Now we know here that that's not a good thing to do, but maybe we're not thinking, and maybe we want to just see what happens if we try. That's perfectly okay. So we're going to put the coordinates of these 4 points into this equation, and we're going to represent it by an augmented matrix. Well, the augmented matrix is going to turn out to just be the same as this matrix, except we won't have the first column because we don't have the x cubes. Okay, and you can convince yourself of that. And it doesn't matter that we're using A, B, C, and D here, and we're using A, B, and C here. Obviously, the 16 would be the coefficient of A now, not B, and the 4 would be a coefficient of B, and the coefficient of C would be 1, and the 2 would be on the other side. And I assume everybody can understand that. If not, just start with these 4 points, plug 4, 2 into this, and see that you get this row. See that you get an equation that gives you this row. Plug 3, 1 into this, and see that your equation matches this row, and then do the same thing for your other 2 points. Now, what does this matrix reduce to? Well, one thing it could reduce to would be this. Okay, we can reduce this first row down to where we have a 1 in front of it and zeros below. Then we can get a 1 in the second row, second position, second row, second column, and use that to get rid of any numbers above and below it and get our zeros here. And we can do the same thing now with the number here, which by the time we've done some reduction will no longer be 1, but we get a 1 here, one way or another, and then we use it to take care of everything above and below. And then, well, we've got what we've got when we get to our last row. And maybe that last row reduces down to all zeros, but probably it doesn't. And if it doesn't, what does that tell us? If it does, what does that tell us? Well, if the last row doesn't reduce to where we have 3 zeros, well, we have all zeros, that means it's going to reduce to where we have 3 zeros and some number on the right-hand side of the equal, which means that 0 is going to equal something that's not 0. And that tells us that we don't have a valid solution. Okay, it tells us that the numbers, we will get numbers A, B, and C from these first 3 equations, but they won't give us a model that fits all 4 points. Now, we already knew we weren't going to be able to get a model that fits all 4 points. This is how we can tell. Okay, if we get a 0 equals non-zero here, not going to work. Now, it is possible that we could have 4 points that all lie on the same parabola. Maybe this 4th point here lies on the parabola through these 3. So maybe we have a point that's maybe here and really does lie on the parabola. If that happened, then our last row would be consistent. 0 would equal 0, rather than inconsistent, 0 equal to something that isn't 0. So if our 4 points are consistent with a quadratic model, which in general they would not be, but they could be, if they are consistent with a quadratic model, then we're going to be fine. We just reduce this system and we get something like this, and the last row doesn't give us a contradiction. Okay? But when we reduce an augmented matrix that has 4 equations with only 3 unknowns, we pretty much expect that our last row, when we finish reducing and wipe out all our first 3 coefficients, is going to give us something inconsistent. Okay? could give us something consistent, but if the numbers are just randomly chosen, it's entirely unlikely that it will. Okay? Now there are other possibilities. This matrix might have reduced to something like this. And you might ask yourself what that means. That means, okay, we know what the value of C is. Okay? The value of A depends on the value of B. And we don't know. We don't have specific values for A and B, which means that we're not going to be able to have a specific quadratic model in this case. In other applications, this might mean something different. In any case, we know how to write the system. We know how to write the augmented matrix. We know how to reduce the matrix. And we know this and this interpretation and this interpretation. And I'll just make a little note here that you can use for reference. This is inconsistent. And the model won't fit all 4 points. Okay, that's what this tells us. This is consistent model. All 4 points just happen to lie on the same parabola. I don't know if you can read parabola. I didn't have a lot of room there. Okay? Make sure you understand those 2 statements and how they relate to the reduced matrix.